Um, Good afternoon, guys. Just let me know if you all can hear me, please. All right, cool. Right. Now, what I'm going to try to run through quickly today, right? Um, we're going to try radioactivity and the specific topics that CXE wants us to know with respect to electricity and magnetism, right? So we're going to start off with radioactivity first, actually, right? Now, the first thing you guys need to know, you need to know about an atom, right? Now, when it comes to an atom has a nucleus, right? And inside of that nucleus, we have, so here, this is a simple diagram of an atom. This here is my nucleus, right? Now inside of the nucleus, we have two particles inside of the nucleus. One, we have protons, right? Two, we have neutrons inside of there, right? These are two particles found inside of the nucleus, right? Then outside of the nucleus, we have other particles here, right? That orbit my nucleus, right? These particles on the outside here that orbit the nucleus are called electrons, right? These are called electrons. So these are the three particles found inside of an atom, right? Apart from that, you guys need to know about the masses and the charges, right? So let's see. Let's go for, let's say I have relative charge, right? And let's say I have relative mass, right? And we have our protons, right? We have neutrons, and we have electrons, right? So apart from knowing the location of these things, right? So the protons and neutrons are found inside the nucleus. That's where we find protons and neutrons. And electrons orbit the nucleus, right? Now, you all need to be able to give the relative charge and the relative mass. Now, notice the word relative, right? Notice this word here. If I were to ask you the relative charge of a proton, you will tell me that the relative charge is positive 1. In the case of a neutron has no charge, right? So the relative charge is 0. In the case of an electron now, it has a negative charge. So it has a relative charge of -1. Now, when it comes to mass now, the mass of a proton, the relative mass that is, we say the mass is 1. In the case of a neutron, the relative mass is also 1. But in the case of an electron, the relative mass is 1 over 1840. So you all need to know this table, right? For both physics and chemistry, right? You need to know this. Now, I use the word relative here, but the actual charge on, let's say, right? You're not supposed to, you don't have to learn this off, guys. So actual charge of, let's say, an electron, right? The actual charge in coulombs is something like this, minus 1.6 by 10 to the minus 19 coulombs. Now, you are not expected to learn off these numbers, but what I'm trying to tell you, there's a difference between relative charge, relative mass, and actual charge and actual mass. So the actual charge on an electron is this figure here, right? But the relative charge is -1. We just use -1 here, right? So you need to know this table. You need to know the location of these particles inside of my atom. Now, we need to be familiar with something called nuclear instability, right? So there are atoms that are unstable, and because they are unstable, they can emit one of three different particles, right? So there are three radioactive particles that you guys need to be familiar with, right? And these particles, right, are what we call alpha particles. So we have something called alpha particles, right? We have something called beta particles. Right? And we have something called gamma rays, right? So gamma rays. Now you need to know what each one of these things are. In the case of an alpha particle, CSEC can ask you, what is an alpha particle? An alpha particle is a helium nuclei. Right? That's what an alpha particle is. It's a helium nuclei. And normally we represent it like this, He42, right? Or we can use this to represent an alpha particle. That's a Greek symbol, right? So an alpha particle is simply a helium nuclei. Think of it as a helium atom that has lost 2 electrons. That's essentially what it is. It's a helium atom that has lost 2 electrons. That's what it is, right? Now, in the case of a beta particle now, you all need to know what a beta particle is. CSEC can ask you that. A beta particle is a fast moving electron. So it's a fast moving electron, right? That's what it is. It's a fast moving electron. Now in terms of symbols, right, a beta particle could be represented by this, E0 minus 1, or we can simply put this symbol here, which is a Greek symbol for a beta particle, right? Now, in the case of gamma rays are part of your electromagnetic spectrum, right? So it's an electromagnetic wave. That is what gamma rays are, right? So it's an electromagnetic right? That's what it is. That's what gamma rays are. They are electromagnetic waves, right? In terms of my symbol, the symbol that I use looks like this, right? That's a symbol for gamma rays. Now, there are certain things they can ask you concerning this. They can ask you about the ionizing properties of each of these 3 particles, right? So when we say ionizing, when radiation passes through matter, what it does, it knocks electrons out of matter, right? So therefore it causes matter to become charged. Alpha particles are the most or the strongest ionizer, right? So alpha particles have the strongest ionizing capabilities, right? So if I were to compare these 3 here, I will say alpha is the most ionizing, right? Beta is going to be a little less ionizing than alpha particles, and gamma radiation is the least ionizing of all 3 radiation. So you need to know about the ionizing properties of these particles. So make sure you understand this. If a radioactive particle is passing through matter, and when you say matter, that can mean air or it can be through a material. As fast as these particles pass through the material, it's knocking electrons out of the material. Anytime something loses electrons, it becomes positively charged or it becomes ionized. So therefore, if an alpha particle is passing through air, it's going to ionize air. If a beta particle is passing through air, it's going to ionize air. Same thing for a gamma ray. Now, we need to compare the ionizing properties. So just remember this. Alpha particles are the strongest ionizers, right? Gamma radiation is the least ionizing out of the 3 radiation, right? So that's one thing you need to be aware of, ionizing properties. The next thing you need to be aware of is the charge of these particles. Alpha particles have a +2 charge, right? So alpha particles have a +2 charge, right? Beta particles, it's a fast moving electron. So therefore it has a -1 charge, right? So it has a negative charge and it has less charge than the alpha particles. You see that +2 charge on the alpha particle? That is what makes it so strong an ionizer, right? And in the case of gamma rays, right? Gamma radiation has no charge, right? Gamma radiation has no charge, right? Now, the fact that the charges are different on all these 3 particles it affects what happens when they move in an electric and a magnetic field, right? So you need to know about the charge, right? You need to know about the ionizing abilities, and you need to know what these particles are, right? I'm going to come back to them in a sec, right? Just one more thing I want to tell you guys about these particles. So these particles have a range in air, right? Alpha particles, because they are so ionizing, they only travel a few centimeters in air, right? So alpha particles, if you want to stop alpha particles, a sheet of paper can block alpha particles. So if you have an alpha source in front of you here, and you standing up here, if you just put a sheet of paper between you and the source, you're going to stop most of those alpha particles from actually reaching you, right? In terms of the impact on your body, if you were to put an alpha particle right next to your hand or something here, right? You put an alpha particle here. What the alpha particle is going to do, it's going to burn the surface of your skin, right? It's going to be stopped by the skin, but all that energy is going to be given up at the surface of the skin, right? So alpha particles are dangerous. Another thing about alpha particles, if you swallow something that is emitting alpha particles, it's going to destroy some of your organs inside your body, right? So alpha particles could be dangerous if ingested, right? Now, beta particles, they travel a little more than alpha particles. However, if you take a sheet of aluminum foil, you can block beta particles, right? So beta particles can travel further than alpha particles, but if you have a thin sheet of aluminum foil, you can stop most of them from coming towards you, right? Now, gamma rays now, on the other hand, they are very penetrating. They can travel long distances in air or even matter, right? So if you wanted to stop gamma radiation, you need either a thick lead shield or you need a thick layer of concrete in order to prevent gamma radiation from coming towards you, right? So gamma ray, if you're standing up right here and you have a gamma source in front of you, that gamma radiation is just going to pass through your body, right? So gamma radiation is very dangerous because it can pass through your body, which means it can impact the cells inside of your body, right? So these are some things you need to know about the three particles, right? Right, somebody's asking me about if CXC will accept those definitions. Yes, those are the definitions that CXC requires, right? Now, there's something here that I want to make sure you guys know about, right? Now, we have something called radioisotopes, and those are, now an isotope, let me just, hold on, let me get a blank slide here, right? So we have something called an isotope, right? Now you all need to make sure you know the definitions for some of these terms, right? Now if you want to represent an element, right? Normally we have a symbol for the element. So let's say Na, that's sodium, 2311, right? That's sodium. We can have something else that looks like this, sodium, and you might see 24 and 11, right? These here, right, are what we call isotopes, right? Those are isotopes. Now isotopes, well, first things first, right? You need to know what this number on top here means. That number there is called my mass number, right? This number here at the bottom here is called my atomic number, right? Now, if you have the same atomic number but different mass number, then you are isotopes of the same element. You have sodium 23 and sodium 24 here, right? So the mass numbers, look at this. This is 23 and this is 24. So the mass numbers are different, but the atomic numbers here are the same. So these two are what we call isotopes. So isotopes have the same atomic number but different mass number, right? That's one way you can say the definition, right? So same atomic number but different mass number, right? Another way you can give this definition is you can say the same number of protons but different number of neutrons. Right? This is another way you can state your definition. Right? The preferred one is actually this one here. Same number of protons but different number of neutrons. Right? Now, when we have something called radioisotopes, right, they decay over time. Now, there is a definition that you guys need to make sure you know, right? And sometimes I tell students the definition and they still write the wrong thing in the exam, right? So we have something called my half-life, and that is important. You all need to be able to define what is meant by the term half-life, right? So make sure you know this for the exam. What is half-life? So your half-life is the average time taken for the activity, right, to decrease by half its initial value. Right? It's a clear, simple definition, but please make sure you give it word for word. Don't go and give the people something else, right? It's the average time taken for the activity to decrease by half its initial value, right? That's the definition for my half-life. Now I'm going to show you how to determine half-life, the kinds of questions that actually come in the exam, right? But please, you need to know your definition. You need to learn this off. When it comes to physics, in terms of how they bring the exam questions, you have definitions. Your definitions needs to be precise. No old talk, right? Right? Your definition, they have to be precise in order to get full marks. And you're going to get calculations and you might get some application of some theory, right? That's essentially how the exam paper or how the exam questions come. Now, let's look at a question here. Let's look at this first question here. The activity of a radioisotope is 120 becquerels, right? So activity could be measured in s to the minus 1, right, per second, or sometimes you see a unit called the becquerel, right? So the activity of a radioisotope is 120 becquerels. After 24 minutes, the activity of the radioisotope decreases to 15 becquerels. What is the half-life of the radioisotope? Now you can be given a question like this in the exam and they could give you up to 5 marks to work this out, right? It's an easy 5-mark question if you know what you're doing. Now, there are formulas to work this out, but at your level, at the CSEC level, you don't need to learn any formula, right? It's a very simple way we can work this question. So let's look at this question here. So you're starting off with 120 becquerels, right? That's my initial activity. Now, if you understand what the concept of half-life is, all we are doing is keep decreasing by half my value, right? So if my initial activity is 120, right? After one half-life, it's going to be half of that value, which is going to be 60 becquerels, right? So after one half-life, so I'm going to just label this. This here is one half-life, right? So the time taken to go from 120 to 60 is one half-life. Then if I decrease this by half again, right? That is going to be a second half-life, right? 60 divided by 2, I'm going to go to 30 becquerels, right? Now look at what it's saying. The time taken to go to 15 is 24 minutes. So what I'm going to do now, I'm going to decrease this by a next half-life. So half of 30 is going to give me 15 becquerels, right? So therefore, I have gone through another half-life. Now remember, half-life is a time interval here, guys. That's what it is. Now, watch what's happening here. The question says that I am going from 120 to 15 becquerels, and the time taken for me to do that is 24 minutes. So this here is a total time of 24 minutes, right? Now if you look at this diagram here, I've actually gone through 3 half-lives, right? So therefore, 3 multiplied by my half-life, right, is actually equal to 24. So therefore, my half-life is going to be equal to 24 divided by 3. So therefore, my half-life is going to be 8. And please use whatever time they gave you here. It's minutes, so therefore it's going to be 8 minutes. Right? So this is how we work a question like this if they give us a time interval. Right? Where we know what the initial activity was and we know what the final activity is. Right? So I'm hoping you all followed what just happened here, right? Now let me do the second one for you guys here, all right? Right, so this is another way they can ask the question here. So they told us the half-life. The half-life of a radioisotope is 4 days. So you know what T1/2 is, right? So T1/2 is equal to 4 days. Now the initial mass of the sample is 120 grams, right? 120 grams. What is the mass of the sample after 20 days, right? Now, here's what you have to do in a question like this. You know what the half-life is. It's 4 days. You know the total time interval we are concerned about. It's 20 days. So the first thing we should really do is to figure out how many half-lives have passed in 20 days. So number of half-lives, right, is going to be equal. You need to take your total time, which is the 20 days, and divide it by 4, and that's going to give me 5 half-lives, right? So this sample is undergoing some change within a period of 5 half-lives. So to work this question, all we need to do, we need to start off at 120 grams, right? So every arrow that I draw represents 1 half-life. So what's going to happen here is after 1 half-life, I'm going to have 60 grams. So that's 1 half-life I just passed through here. Then I'm going to go through a second half-life, and half of that is going to give me 30 grams, right? Then half of this is going to give me 15 grams, right? So all I've done here, I've gone through 3 half-lives. Let's go through a fourth one again. Remember, every arrow represents a half-life, right? So half of 15 is going to give me 7.5 grams. So that's 4 half-lives. So I need to go through 1 half-life again. So half of 7.5, right? So use your calculator for that. 7.5 divided by 2 is going to give me 3.75 grams. So look at carefully. This is 1 half-life. This is 2 half-lives. This is 3 half-lives, 4 half-lives, 5 half-lives. So my answer, right? My actual mass. So the mass after 20 days, right, is going to be 3.75 grams. That's going to be my half-life after that period of time, right? Alright, so if you all haven't done so as yet, please hit like and subscribe to my channel, right? You can share these free sessions if you want to with your friends, that's fine, right? right? So just to give you all a reminder, yes, I do give online maths, maths, physics, and chemistry classes, right? All my new classes are going to start in August, right? I can be contacted via WhatsApp on this number here, or you can send an email if you want to, right? So just for those of you first time you're joining here, my name is Terry David, right? I'm a past national scholarship winner here in Trinidad, right? I'm also the author of all these books here, the official CAPE Physics Study Guides for CXC. Those are the books that are actually on the syllabus. So I am the sole author of these books here, right? I also have a workbook out there and a workbook for maths, and there's a multiple choice maths book as well, right? So you may have seen some of those books around, right? I am the author of those books. Now, the other way they can ask you guys, right, about half-life is they can give you a graph. And if they give you a graph, you all need to know how to measure half-life from a graph, right? That's something you all need to know. How do we measure half-life from a graph, right? Now, in order to do that, what we need to do, we need to select a starting point. Look at what I have plotted here. I have activity against time. Now your time, if they give you a graph, the time could be in seconds, it could be in minutes, it could be in hours, it could be in days. So keep that in mind, right? So pay attention to the unit for time on a graph like this. This particular graph is what we call an exponential graph, right? So basically, I'm looking at activity here and it's decreasing over time. Instead of plotting activity, right, CXC can also give you mass in grams, right? So they can give you any one of those here, but the concepts remain the same, right? So what you need to do, you need to select what is your initial activity here. In this case, if you look at my graph, I'm starting off at 12, right? Now, if I want to measure the half-life from this graph, all I need to do is to take my initial activity of 12 and divide it by 2. If you divide 12 by 2, you're going to get 6, right? So therefore, my activity is falling or decreasing by half. So what you're going to do, you're going to go to the graph and you're going to draw a line. By the way, CXC asks you to draw the line sometimes. And you're going to read off that time at the bottom here, right? That's what you're going to do. You're going to read off this time here. So based on that there, I can see that my half-life, right, is actually equal to 2. In this case here, it's 2 seconds, right? So I've measured my half-life already. Now I have seen CXC bring a question for about 25 marks. I'm basically asking you to do this several times, right? So if you just wanted to measure it from the graph, just start at 12, find half of 12, which is 6, and then you read off that time interval. But we can do this more than once. So if my activity is now at 6, let's decrease that by half again. So 6 divided by 2 is going to give me an activity of 3. So what I'm going to do, I'm going to go across here and I'm going to read off this time here, right? Now the time that I'm getting here is 4 seconds, but the time that I'm interested in, right, is this time interval here, the time from 2 to 4. So therefore, this period here is my half-life. So my half-life is 4 minus 2. Right? So again, I'm getting a half-life of 2 seconds, right? We can do it a third time if you want. So you start off with 3. If you divide that by 2, you're going to get 1.5. So 1.5 is somewhere here. This here is 1.5. So if you want to read off from your graph, you're going to go across here, right? Now normally in class, I'll take my time and do this, right? But I don't have that much time here. So look at what's going on here. I'm getting, this is corresponding to 6 seconds. So my half-life has to be the difference between this 6 seconds and this 4 seconds here. So this here is my half-life again. So you notice I'm getting 2 seconds again. So no matter what I do, I'm getting a half-life of 2 seconds, right? So keep that in mind. You all need to know how to measure half-life from a graph, right? Now, apart from that, you all need to know something else as well. Hold on a sec, right? I need to get a blank slide here. Now, I notice I have some students here, are students from my online class, right? So hopefully they should remember how to do these things. So I'm going to ask you all something. When you actually do an experiment like this, right? this is the kind of graph that you're going to get. The graph is going to look like this, right? Now, there are two features about this graph here that you need to be familiar with. The first thing here is that if you notice the graph, it is not a smooth curve. Why is this graph not a smooth curve? That's an exam question. Why is that graph not a smooth curve? Those of you in my class should be able to answer this, right? I see Liana here. I see Zachariah here. Who else from my class here? Right, so Melissa Taylor, that is absolutely correct, right? I saw somebody telling students that it's experimental error. That is absolutely wrong, right? So it's not experimental error, it's that radioactivity is a random process. So radioactivity is a random process. That's the answer that CXC wants, right? Don't tell them experimental error. That is wrong, right? It's a random process. Now, what a random process really means is that if you have a radioactive sample, so you have a sample here with one set of nucleus inside it, right? So you have a sample of, let's say, chlorine 37 or iodine 131. That's a radioisotope, right? What that means is if I sit here and I am watching this sample, I cannot possibly predict which atom is going to decay. That's what it means, right? It's a random process. You cannot predict which atom is actually going to decay, right? What we can do something called statistical analysis, and we can say something about all of the atoms, right? That's what we can do. Now, our next feature about this graph here, the graph actually never reaches to zero, right? The graph never reaches to zero. So something is happening here. Why doesn't the graph reach zero, right? Why doesn't the graph reach zero? So if you are asked this question in the exam, what you're going to say? Why doesn't the graph go to zero? I've seen one answer here, not all of the atoms decay. That's not what we're looking for. So let me show you all something. If you have a sample, right? Let's say you have a radioactive sample here, right? And you have what we call a GM tube, right? So you have a GM tube, right? When I put that source in front of the GM tube, I'm going to get this clicking sound, right? So you all have, I'm sure you all have seen movies where they have a, what they call a Geiger counter, and they put it close to a radioactive source, and you're hearing clicking sound, right? Now, what is happening here is that the particles are decaying, right? But after a while, right, even if all the particles decay, you're still getting some radiation. That radiation there, right, is called background radiation, right? That's what it's called. It's called background radiation, right? So background radiation is there no matter what. I am sitting here and background radiation is around me all the time, right? Sometimes they ask you for the source of the background radiation. So background radiation comes from rocks within the earth, that's one source, right? They come from outer space as cosmic radiation. So there's radiation hitting the earth all the time. That's background radiation, right? You also get background radiation from radioactive power plants, right? Or nuclear power plants, I mean, right? So there is radiation around us all the time, and it's called background radiation. So that graph actually never goes to zero, right? It never goes to zero, and that's why, right? Right, so that's the reason for that there, right? Now, where am I now? So there's some other things you need to know. So let's just cover that quickly, right? Now, here's what's happening here. You all need to know what happens to alpha, beta, and gamma when it passes through an electric field or a magnetic field, right? I'm gonna do the electric field first. That's the easier one to do, right? Now, an electric field, right, is simply to set up an electric field. It's easy to do that. All you can do is do this. You have two plates, right, and we have a battery, and what we do, we connect one end. This is my positive terminal of the battery, right, and you connect it like this, right? And what we can do, we can create a field, right? So this is my electric field here, right? So what we are doing here, we have a radioactive source, right? That's this here, that's this thing here, right? And they said, draw the three rays as they pass through. So we're looking to see what happens to alpha, what happens to beta, and what happens to gamma. Now, to predict what's going to happen here, right? What we do, we need to understand what charge is on each of these particles. Now, gamma radiation is the easiest one to draw because, now let me use a different color here. So gamma radiation, it has no charge. So therefore, what's going to happen is that gamma radiation is going to be undeviated. So if it's moving this way, right, this here is going to be my gamma radiation. Nothing is going to happen, right? No change in direction. I know my line looking kind of slanted, but no change in direction, right? Now, when it comes to the other two particles now, let's do alpha particles. Alpha particles are positively charged, right? So this is what we need to know. So alpha, right, has a positive charge, beta has a negative charge, and gamma has no charge, right? Now, if you have an alpha particle passing through an electric field, what's going to happen is that the alpha particle, because it's positively charged, it's going to deflect towards this here, right? Towards the negative side of my electric field. So therefore, this here is what's going to happen to alpha particles, right? Now, beta particles are negatively charged. So what's going to happen? Let's use a different color here. Beta particles are negatively charged. So what's going to happen? They're going to move towards my positive side of my, so it's going to do this, right? So here is going to be my beta particles. So you all need to know this diagram. Please make sure you know this diagram, right? So the alpha particles are deflected towards the negative plate. The beta particles move towards the positive plate, and the gamma radiation, it just passes straight through. It's undeviated, right? So you all need to be familiar with that diagram. I just need to borrow this hand here, right? This is important here. Now let's go back to this guy across here, right? This is the one that students have some trouble with, right? Now, when you want to predict the direction of a particle in a magnetic field, right? There's certain things that you need to know. In order to do that, to predict the direction, I need to use something called Fleming's left-hand rule, right? Now, I'm not sure how you all see in my image here, but this is my left hand that I'm holding up, right? This is my left hand, right? You all should have done this in school or in your classes where we're going, right? Now, this here is my left hand. There are three fingers that are important when it comes to my left hand rule. My thumb, that gives me the direction of my force. my index finger or my pointing finger gives me the direction of my magnetic field. And the second finger, right, gives you the direction of the current. So you all need to be familiar. You need to understand how to use this left-hand ruler. Make sure you know how to do that. So here's what we're doing here. So on this diagram, so this here gives me the direction of my force. So let's put in those things here, right? This here, my thumb, gives the direction of my force. My second finger is the direction of my field. And it goes like this, north, south. So this here is my field, right? That's my magnetic field. And this second finger here is my current. So this gives me the direction of my current, right? This is important. It's extremely, extremely important. Now here's what's happening here. Again, you have a radioactive source that has all three particles inside here. And you want to draw the path taken by each of them. Now, let's deal with the first one, which is the easiest one. Nothing happens to my gamma rays, right? Nothing happens to my gamma rays. So gamma radiation is going through this magnetic field and nothing is going to happen to it. So this here is gamma radiation. And the reason why it's undeflected is because it has no charge, right? If a particle is uncharged, it's not going to be deflected in a magnetic field. Now here it is. You all need to understand this diagram. You see these X's here, these things here. That gives you the direction of the magnetic field. And here's what the question is saying. The question says, these particles are subjected to a uniform field perpendicular to their path, right? Now, every time we use an X to represent a magnetic field, it means that the magnetic field is going into the screen. So you're all watching my screen right now, right? So the magnetic field is going into the paper or into the slide, right? So here's what's going to happen. And there's something you all need to know. When you have, right? So some of you all may or may not know this. If I have a positively charged particle moving this way, right? It means that my current is also moving in that direction. If, however, you have a negatively charged particle moving this way, the actual current is in the opposite direction. So you all need to know that, right? Hoping you all see that on my screen. Yeah. So if a positive particle is moving from left to right, the current is in the same direction. If a negatively charged particle is moving from left to right, it means the current is going in the opposite direction. That's something you need to pay attention to because you need that knowledge in order to answer this question, right? So here's what I'm going to do now. Let's erase this here. Right, so this is the one that gives students trouble. What did I use for alpha particles just now? The red? Okay, so here's what's going to happen. So I'm going to use my left-hand rule in order to do this, right? So I need to take my index finger. So let me get the screen so I can see what, right? So I have my left hand here, right? The field is into the paper or into your screen. So therefore, I need to point my index finger into the screen, right? Now we're tackling the alpha particle first, right? So if you have an alpha, oh, sorry, yeah. One sec. I'm looking at the wrong. So let's make sure we understand this first, right? So if an alpha particle is moving upwards, so let's say this is an alpha particle, it means that my current is going to be in that direction. But if you have a beta particle moving upwards here, right? It means that the current is actually flowing this way, right? The current is flowing in the opposite direction. So let's tackle the alpha particle first. So the field is into the paper or the screen, right? The second finger gives you the direction of the current. So that means the current for the alpha particle is actually moving upwards. So if you position your hand, you realize the force is moving to the left. So what's going to happen is this. Your alpha particle is going to move this way, right? This here is the direction of my alpha particle. Now, if you work out the direction of the alpha particle, working out the direction for the beta particle is just the opposite, right? But I'm going to use my left hand again. So the field is into the paper, right? Your current, in this case, if the beta particle is moving upwards, the current is downwards. So if I reposition my hand, I realize that my thumb is pointing to the right hand side. So what's going to happen here, so let's use a different color here. I think I had a green for this one. So what's going to happen is the beta particle is going to do this, right, my beta particle is going to move in that direction. Now, if CXC gives you this in the exam, I am telling you, you're getting 3 marks for this. Don't go in the exam and lose 3 marks for this. The same thing for the previous one, right? The same thing for the previous one. This one here is also 3 marks. You're getting 1 mark for each of the lines that you are drawing, right? So make sure you know how to work this out. All right, somebody's asking about maths, right? I have a next math session next week, Tuesday, right? Next week, Tuesday, I have a next math session, guys. All right, so that's what you need to know. Where are we? What's the time? Right. So here what? Let's look at a few exam questions here, and let's see if we can do them quickly. So let's see. One isotope of lead. So this is an isotope of lead. It is not stable, right? But can undergo exactly 3 distinct decays of an alpha or beta or to become stable lead. With reference to the information in the table, write a possible sequence of 3 nuclear equations that can result in stable. So you want to get to this compound here, right? But you're starting from this, right? And they gave us some elements here. They gave us bismuth and polonium, right? So they gave us some atomic numbers. So what they want us to do is to write a possible sequence of 3 nuclear equations in order to end up with 206, right? So let's see. So if we start off, now this one might be a little trial and error here, right? So these are what we call nuclear reactions, right? So you have lead 210, 82, right? And what's going to happen, they said it can undergo exactly 3 distinct decays of an alpha or beta particle. So we want 3 reactions in order to end up with this here, lead 206, right? So what could happen here is that I can go from, let's say if we emit an alpha particle. If you emit an alpha particle, right, this is He42, right? Now you need to balance your mass numbers, right? So let's see. Okay, so we have nothing with 206, right? If this is ET, so okay, I can't use that one, right? I can't just go straight to alpha. That won't work, right? Let me see something here. If I put a beta particle here, which could be represented by this 0, -1, then I can put a particle here that has 83 and a mass number of 210, right? So therefore, if we look at the table, this could be bismuth, right? So this is one possible reaction. So I get bismuth here. The next thing, I can use another bismuth, which is 210, 83, right? And I'm going to decay again. Now, according to the table, I can get polonium, which is 84. So we can probably do something like this. 210, right? And put 84 here, right? And this is PO plus a next beta particle, 0, -1, right? Now, I'm still not there as yet. I have to end up with 206. So let's start with polonium now, which is 210, right? 84. And I'm going to decay again. And let's put an alpha particle here, He42, right? In order for this equation to be balanced here, I can put, let's see if I put lead here, and I put 206. And this here could be 82. Right? So this here represents my answer, and look how many marks, 6 marks for this. Now when you're writing nuclear reactions, your total mass on your left hand side must equal to the total mass on the right hand side, right? Your total mass on the left hand side must equal the total mass on the right hand side. Same thing for the atomic numbers. The atomic number on the left hand side must equal the total atomic number on the right hand side. right? So here's what you really need to know. If I have something like this, right? A, and I have P, and I have Q, and that decays to give me B, right? Plus C, and let's say this is PQ, this is R, this is S, this is T, and this is U, right? In order for this equation to make sense, you see your mass numbers, your numbers on top. P on the left hand side must equal to R plus T on the right hand side. This must hold true, right? At the bottom, when we're looking at the atomic numbers, Q on the left hand side must equal to S plus U, right? So this is the key thing that you all need to remember when you are writing nuclear reactions, right? Now what I did here in this question, now I know I'm moving a little fast, right? We started off with this. This is what you're starting off with here. And it said it's not stable, meaning that it's going to decay, right? But if you, and they already told us, it said there are 3 nuclear reactions taking place in order for me to end up with this. So what I was doing here is trying to decay, either let it emit a beta particle or an alpha particle, right? But I need to make sure I have 3 reactions in order to do that. So there are some more examples, some more exam questions here we can look at. So don't worry, I'll give you some more just now. And I see some of you all asking me about the left-hand rule. Well, I still have to explain how the DC motor works. So I'm going to come back to that in a sec, right? Now, let's look at part C of this question here. They said calculate the energy given off in a nuclear reaction if your change in mass is 0.2014 U. Now, sometimes they ask us to calculate the energy changes in a nuclear reaction, and this is the formula that we have to use, E = mc squared. And that is Einstein's equation, right? Now, in this question here, they told us the change in the mass. It is 0.2014. So M is equal to 0.2014 U, right? But just remember, in this formula here, that mass has to be in kilograms. This has to be in kilograms. I see students taking these numbers here and plugging it into the formula. That's incorrect. CSEC gave us some information here. They gave us what U is and what C is, the speed of light. So U is equal to 1.6, how much they give it as? 1.66 by 10 to the minus 27. 1.66 by 10 to the minus 27 kilograms. And they gave us the speed of light as being 3 by 10 to the 8 meters per second. Please, this here is the speed of light. I see students telling me it is specific heat capacity. That's wrong, right? That is the speed of light, right? Now, how are we going to use that to figure out how much energy is released in the reaction? First things first, I need to convert this mass into kilograms. So my mass in kilograms, all I need to do is to take the 0.2014 and I'm going to multiply that by 1.66 by 10 to the minus 27, right? Now, I'm going to show you all something here. One of the biggest challenges that physics students have is that they have no idea how to use their calculator, right? That's a big problem for students. So here's what's happening here. I'm going to press 0.2014 multiplied. Now this is how you put in this in your calculator. 1.66. There's a button that allows me to get that 10 to the minus 27. That is this button here, the EXP. Press that. And all you need to do is to press 27 and press your plus or minus sign. That's how we enter 1.66 by 10 to the minus 27 in the calculator. That's a big challenge for many students, right? They don't know how to use their calculator. Equal, and this is my answer here. Now the answer that I'm going to get here is 3.34324. So 3.324 by 10 to the minus 28 kilograms, right? So that's my mass here. Now I'm not going to round up the answer because the energy changes that we're working out are extremely small. So I'm just going to shift this a little way here. So my energy released in this reaction, I'm going to take that number, 3.34324 by 10 to the minus 28, and I'm going to multiply that by, look at what the formula is saying. It is saying c squared, the speed of light squared. So it's 3 by 10 to the power 8, but I have to remember to square this. That's a next mistake that students make. They forget to square the speed of light, right? Oh, sorry, I just realized, sorry about that. The calculator was blocking, right? Now, here's how you're working this out in your calculator, right? So I already have the 3.34324 by 10 to the minus 28 multiplied by 3 exp 8, but I need to square that. So students forget to square this. So hit squared and you get this. So your answer, and now I can give my answer as 3 by 10 to the minus 11 if I want, right? So I'm going to give my answer as 3 by 10 to the minus 11 joules, right? So this is how you work a question like this. All right, so I have, there's something here. Let me do this one first here, right? So in this figure here, right, we have a structure of an atom of element X. So they've drawn an atom for us. They told us the ends represent neutrons, this represents protons, and this represents electrons, right? And look, they are telling us how many we have inside of the nucleus. In part 1, they said state the mass number, atomic number. So they want several things. They want the mass number, they want the atomic number, and they want the charge on the nucleus, right? Could you all tell me what is the mass number? Let me just remove the calculator here. We don't need that right now. So tell me, what is the mass number here, guys? All right, so I've seen you all saying 11, right? So to get the mass number, all we need to do is to add up the number of protons and neutrons. So my mass number, right, is simply equal to 5 plus 6, and you're going to get 11. So my mass number is 11. What is my atomic number? So look at the diagram. What is my atomic number? All right, so I seen you all saying 5. So your atomic number is simply how many protons you have. You have 5 protons. So my atomic number here is 5. That's correct. And what about the last part? What is the charge on the nucleus? What is my charge on my nucleus? All right, you all give me good answers here, man. You all say neutral. That's correct. All right, the charge is 0. The charge is 0. And how do I know that? I need to look at how many protons I have. So you have 5 protons, right? So therefore, remember, protons are positively charged, right? So therefore, you have, this is positively charged. So you have 5 protons. And if we look at electrons, you have 1, 2, 3, 4, 5 electrons. So you have 5 electrons. So remember, electrons are negatively charged, right? Electrons are negatively charged. So therefore, you have 5 positive charge and 5 negative charges. So my charge on the nucleus is 0, right? Now, they said, write the symbol for another possible isotope of X. Now, based on the information we have here, we can write down what X is supposed to look like. You know the mass number is 11, and you know the atomic number is 5, right? So if you want to write an isotope, right? If you want to write an isotope, all you need to do is to make sure you have the same atomic number of 5, and you can just change the mass number. Either you increase the mass number or you decrease the mass number. So this could be 12, right? Or I can do something like this, X 10, 5. So these are possible isotopes here, right? They have the same atomic number but different mass number, right? Right? So I'm going to move on to some other things that you all require or you need to know, right? Now, when it comes to an electric current, guys, right? When it comes to an electric current, we have 2 kinds of electric currents, right? We have something called direct current, or what we call DC, right? And we have something called AC, which is alternating current. Now, you all have to be able to state the difference between AC and DC, right? Now, direct current, right? With direct current, the electrons are flowing in one direction only, right? CSEC can ask you that. Differentiate between AC and DC. So for direct current, the electrons are flowing in one direction only. When it comes to alternating current, the electrons reverses direction regularly with time, right? So a normal little dry cell, or what we call a battery in your house, right? So the battery in your remote control for your TV, that supplies DC, that's direct current, right? Your car battery in your car, that is direct current, right? The electrons are flowing in one direction only. When it comes to alternating current now, the electrons reverse the direction regularly with time, right? Example of an AC current is your main supply inside your house, right? You see when you plug your TV into the wall or you plug your fridge into the wall, that current there is alternating current, right? So the electrons are reversing direction regularly with time. So you need to differentiate. That's an exam question. Differentiate between AC and DC. So tell them that DC, the electrons flow in one direction only. When it comes to AC, the electrons reverses direction regularly with time. That's the answer, right? Now, let's see what they're asking us here. So you have a waveform shown in figure 4. It depicts a current through a resistor in an AC circuit, right? So they gave us, so you have current, right, versus time in milliseconds. Now, yeah, you have to be careful with this. The first part, they said calculate the period of this wave. What is the period of this wave here? All right, so I've seen some of you all saying 30 milliseconds. That looking, now you need to give the unit. So your period, so period T, that's how we represent period. It is 30 milliseconds, right? It's the time taken for one waveform or one crest, right? So it's from this point here to this point here. That is one period, right? So one period is one waveform. You're looking for one crest and one trough, right? So it's 30 milliseconds. That's the answer for the period. Now, the frequency now. Frequency, there's a formula. Frequency is 1 over my period, right? And that's 1 over. So guys, please, when you're using this formula, that time has to be in seconds. So I can't just put 1 over 30. That'll be wrong. It'll be 30 by 10 to the minus 3, right? Milli, you need to know that prefix. That prefix milli means 10 to the minus 3 or divide by 1,000. So let me show you how you're doing that on the calculator. So what I'm going to do on the calculator, I'm going to take 1 divided by 30 exp, and I'm going to put minus 3 here. And this is what I'm going to get as my frequency. I'm going to get 33.3 hertz, right? 33.3 hertz. So this answer here is 33.3 hertz, right? That's what my answer is for my frequency, right? Surprising, they only gave 3 marks for this. Sometimes when they give you this in the exam, they would have given you something like 5 marks for this, right? So make sure you know how to calculate period and frequency of an alternating current. Now the next part of the question here, if the resistor is 45 ohms, determine the peak-to-peak voltage across the resistor. Now, you have to be careful with this as well. In order to find your voltage, right? So you all should know the formula V is equal to IR. You all need to know this, right? My current in this case here, so let's look at the peak current. My peak current here is 4 amps. So if I take 4 amps and I multiply by my resistance, the resistance in this case here is 45 ohms. So it's 4 multiplied by 45, right? And that's going to give me 180. 4 by 45, yeah, I'm going to get 180. So you're getting 180 volts. But here's the problem. That's not the answer, right? Because they said determine the peak-to-peak voltage. So the voltage is actually doing this. It's going up here and coming back down, right? But the maximum voltage here is actually 180 volts. Therefore, at the bottom here, this here is minus 180. So when they ask you for peak-to-peak, they want this whole that whole distance there. So my voltage, my peak-to-peak voltage is going to be 180 plus an x 180, right? So this is going to give me 360 volts, right? So pay attention to some of the terms that they're using in the questions, right? So it's 180 plus an x 180, right? So it is 360 volts peak-to-peak voltage. So that's the answer for part 2. In the third part now, they said calculate the maximum power dissipated in the resistor, right? Now, we need to know that power, right? Power is equal to I squared R, right? Power is equal to I squared R. That's the formula we're going to use. P is equal to I squared multiplied by R, right? Now, all I want to know is the maximum power. So to get the maximum power, all we need to do, we need to take the maximum current, right? Which is this value here. That corresponds to 4. That's 4 amps. So it's going to be 4 squared multiplied by my resistance, which is 45, right? So this is going to be 4 squared multiplied by 45, and you're going to get 720 watts, right? So these are the kinds of questions it could give you when it comes to AC, right? So P is equal to I squared R. Anytime in physics they ask you for power dissipated, right, you need to use I squared R. You could use P equal IV, right? So if you take 4 and you multiply by 180, right, you should get the same answer, right? But really and truly, you'll get the same answer, but the formula we should be using is I squared R. right? So these are the kinds of questions that can come on AC currents. I think I have a few more here. Yeah, I do. Let me ask you all something here. They want to know what type of current is each of these here. So if you look at this waveform A, is A AC or DC? So just to let you all know, this is the last free physics session I'm having, right? So the question is, what is that current there, right? Now, I've seen some people from my class answering here, right? So when you have a graph, right, and you want to know if a current is AC or DC, if the current stays in one direction, so let's say the waveform itself, it's above your time axis and it never crosses the time axis, that is DC, right? That is DC. So that's how we know if something is AC or DC. This is actually DC. This is not AC, right? The graph, right, it's above my time axis. It never crosses. It's still above my time axis. It's in one direction. So this here is a DC, right? It's a varying DC, but it's still DC, right? And some of you all said rectified. Yes, that's when we rectify an AC. That's how it's going to look, right? So for part A, that's a DC current. What about B? All right, so B is very easy to identify, right? B is very easy. So I see you all saying the answer already. B is a DC, right? A straight horizontal line, that's still DC, right? And then the last one, well, once you see a sine waveform, or what we call a sinusoidal curve, right? This here has to be alternating current because the waveform is above my time axis and below my, my time axis, right? So that's how we know something is an AC from a graph. Right? You should see part of the graph above your time axis and part below the time axis. That's how we know when it's AC, right? Now, this next part here, they want us to determine my period and my frequency. What is the period of waveform C? Zachariah asking if you put rectified AC, they may not necessarily, right? Because they ask you to classify the waves as either AC or DC, right? That's the problem. So if you put rectified AC, that may not give you the mark. You need to be careful when you're working out things like period and frequency, right? Need to be very, very careful. So you need to look at how the axes are labeled, right? Remember, the period is one cycle or one waveform. So we're looking at this waveform here. So therefore, my period T is actually equal to 0.20. And look at, you need to watch the axis here, right? Because sometimes the axis is in seconds and sometimes it's in milliseconds. So it's going to be 0.2 seconds, right? And then to work out the frequency now, my frequency is equal to 1 over t, which is 1 over 0.2 and that's going to give me 1 divided by 0.2. I'm going to get 5 hertz. So this here is 5 hertz, right? So the unit for frequency is hertz. All right, so let me make sure. I need to give you all something here quickly, right? I have another question here, right? Another AC question, but I want to get to these first. All right, so you all need to know about magnetic fields, right? So you need to know about a bar magnet, right? You need to be able to draw the fields around a bar magnet, right? So if I have a single magnet here, this is what's happening here. The field looks something like this. So you all have to be able to sketch this in the exam. Those lines are called field lines, or sometimes we call them flux lines. But apart from drawing these lines, you all have to be able to put the direction, right? So the direction here, the arrow points away from the North Pole, right? It points away from the North Pole, but towards the South Pole. So this is what my field looks like. And sometimes you might see, they might draw something like this here as well, right? In which case the arrow is pointing this way, right? So you all have to be able to sketch the field around a isolated magnet. The next field you need to be able to draw is if I bring 2 North poles or 2 South poles together, right? You're going to have repulsion. So you need to be able to sketch what happens to the field between 2 North poles. What's going to happen is that the field is going to look like this, right? Now the arrows are important, so you need to put the arrows pointing like this, right? Arrow pointing towards, right? So this is 2 North poles facing each other. And then we also need to draw the field between a North Pole and a South Pole. Right? So this is South, this is North. Right. So what the field line looks like here, well, this is going to be this. Right? And what's going to happen here is you're going to have something looking like this. Right? So North to South. So it's going to do this. Right? This is repulsion and this is towards, right? So you all need to know these field lines. Make sure you know those field lines, right? Yeah, so it's out to the north and into the south. Now CSEC can ask you to define the direction of a North Pole. So if you check the textbook, there is a definition for that. The direction of a magnetic field is the direction of the force on a North Pole placed at that point, right? So if you wanted to figure out the direction of a field, let's say I was at this point here, and I wanted to figure out the direction of that field, pretend that I put a North Pole here. If I put a North Pole here, it is going to be repelled. That's why the direction is going to point this way. If I put a North Pole here, right? So if this was a North Pole, it's going to be attracted to the South Pole. That's why the arrow is pointing this way. So that's an exam question. Define the direction of a magnetic field. It is the direction of the force on a North Pole placed at that point. That's the answer, right? So we need to know these magnetic fields. Next thing we need to know now. Let's look at an exam question here that could be asked. So figure 6, it shows the magnetic field between poles of a strong magnet, right? So between a North Pole and a South Pole, we just have lines going from north to south. That's what it is. Now they want us to complete the following diagrams to show, right, complete the following diagrams, part 1, to show the magnetic field due to a current carrying conductor where the current is directed into the planar paper, right? Now, so for those of you who are aware of how you draw the field lines around a conductor, right? You have to use your right hand grip rule. That's what you need to do. It's called the right-hand grip rule, or sometimes you see the corkscrew rule, right? So the current, so what they've drawn here, they've drawn a piece of wire, but the current is flowing into the paper, into your screen, right? So I have to use my right hand. Now, your thumb points in the direction of the current, so it's into the paper or into the screen. And these fingers, all the other fingers, will give me the direction of the field. Now, in this particular case here, when you have a current carrying conductor, the field lines look like this. They are what we call concentric circles, right? So CXC says you all get in the DC moto, so chances are you may get the same exact question, right? So pay attention to this, right? So it's concentric circles around the wire, but you need to figure out the direction. To do that, you're using your right hand grip rule. Thumb gives you the direction of the current going into the paper, and all the other fingers give you the direction of the current. So what's happening? They're doing this. That's the direction that the field lines will be in, right? Now, what they're leading up to here is a conductor being placed between a magnet. This is the field lines between a magnet. So if you put a conductor inside here, this magnetic field and this magnetic field will interact and the wire will experience a force, right? Which is what they're going to ask you in the next part here. So they said the resultant magnetic field when the current carrying conductor is placed between the poles of a magnet, right? Now, this is basically the principle or what we call the motor effect, right? So, in this particular case here, let me get back my my left hand. Where is that? Let's get back the left hand here, because you need the left hand in order to understand this. Right? I'm using the left hand here. So what's happening here is that the field is from north to south, right? So my index finger is pointing in that direction. My second finger is pointing into the paper. So therefore, the force acting on this wire here is downwards, right? So try to use your left hand rule and see if you're getting that, guys, right? Now, what we need to do, we need to draw what's happening to the field in this diagram here. Now, essentially what's happening here is that the field produced by the wire, which is this, and the field produced by the magnet, they interact. And what's going to happen? The wire is going to experience a force, right? So to draw this diagram here, what you need to do, the combined field looks something like this. So what you need to do, you need to show that the field is close by on this side here, right? So this is what's happening here. So the field lines, they do this, they do this, they do this, they do this, and your force is acting downwards, right? So if you want to just check any textbook and look for this diagram, you need to know this diagram, guys. Right? Now, let me get to this part here where you guys need to be able to explain the operation of a simple DC motor. Right? You all have to be able to explain how a DC motor works. CXC says in the broad topics that you need to know this. Right? Now, they can ask you this question in several ways. They can ask you to sketch a DC motor. That's one thing they can do. Or they can give you a diagram and then they can actually explain how the motor works, right? Now, they have the diagram here already, so I'll use the diagram to explain how the motor works. It's a DC motor, right? So those of you who have any kind of toy at home, right, that has, let's say you have a toy car or something and the toy car is moving, there's a simple DC motor inside of that, right? So with respect to the DC motor, you have a coil that is situated in a magnetic field, right? That's the first thing. Now, the coil has two ends right? And those two ends are connected to something called, look, they have it here. They have it called X here, right? So they said label the part X. So the DC motor has something special called my split ring commutator, right? So there's something called a split ring commutator. There's a reason why there's a split ring commutator. This here is what we call our brushes, right? So those, any devices in your home that uses a DC motor, sometimes you have to replace the brushes, right? Because they get worn over time, right? So those are brushes, those press against the split ring commutator. Now here's what the question asking, right? And by the way, I think this question was something like 9 marks. That's plenty marks, eh? And how continuous rotation is achieved, right? That's a mouthful they're asking you for here. Now, let me do something first for you all. You all have to be able to sketch a DC motor in the exam, quickly in the exam, right? So pay attention to how I'm going to do this. You have to be able to sketch a simple DC motor, right? So this is me trying to sketch it here, right? So this, I need to draw 2 magnets. That's my North Pole, South Pole. And then I need to draw a coil. So to draw the coil, right, what you're going to do, you're going to do this. Really and truly, we just draw 1 coil because we can use that to explain how it works, right? So that's my coil. And if you have to explain how this thing working, label your coil. A, B, C, and D, right? Next thing we're going to do now, we need to connect our split ring. So that split ring is this little thing that looks like a C, right? That's my split ring. After you draw the split ring, you need to draw your brushes, which are these rectangles here we're drawing. So that's my brushes, right? Next thing we're going to do now, we need to connect that to a battery, right? So let's just put a switch in the circuit and let's put a battery here, right? That's essentially what a DC motor is. So if they ask you to draw one in the exam, just draw this, you get full marks for it, but you need to label it, right? So you have your coil. So this here is your coil, right? This is, well, you need to label your brushes, that's this, and you need to label your split ring, right? Now, this here, to explain how this works, that's a handful, right? And you need to make sure and say everything that is required in order to get that mark, right? Now, let me see. I want to get this on the next page. Now, I need to make sure you all understand this. First things first, right? You need to label where your current is entering the coil. This here is my positive terminal. This is my negative terminal. So when you close that switch, that current is going to flow here, flow here. It's going to flow here, right? It's going to flow down here and eventually flow this way. Then it's going to flow here, then flow here, flow this way, right? So the first thing you need to understand the part of the current that is taken. In this question, you need to make sure and mention Fleming's left-hand rule. If you don't mention that, you're going to lose marks. So Fleming's left-hand rule needs to be mentioned here, right? That is required. You need to say that somewhere there, right? Now, look at what's happening here. So you need to tell them when you close the switch, the current flows through this section of your coil CD, right? The current is flowing through the section of that coil CD. Let me ask you all something. That coil or that section CD is going to experience a force. Is that force upward or downward? Make sure you all know this. This, like I tell you, I feel they're going to give you a question like this in the exam. You have to use Fleming's left-hand rule to figure that out. I don't know why Faith removed her answer. The answer is looking right to me. Don't doubt yourself, Faith. You have the correct answer. It's downward. It's going to be a downward force, right? So when you're answering this question, you need to say, when the switch is closed, a current flows in the section. What section is that? Section D to C, right? Therefore, the section DC experiences a downward force according to Fleming's left-hand rule. You see what I just said? That's what you need to say in order to answer that question. So a current flows from D to C. Therefore, that section of the coil experiences a downward force according to Fleming's left-hand rule. So what's happening here? So look at the coil. So let me use a different color here. Let's use blue or something. So this section here is going to experience a downward force. Then the current flows from C to B, right? And then it's going to flow from B to A, right? B to A is going to experience a force. Is that going to be upward or downward? Right, so I've seen everybody saying upward. That's sounding about right to me, eh? That sounds about right to me. So if you use Fleming's left-hand rule, so what you're going to tell them now, you're going to say a current flows through the section B to A. Therefore, it experiences, and you're going to tell them it experiences an upward force. So this wire AB here is going to experience an upward force, right? Now, these two forces are equal and opposite in direction. So if one is 10 newtons, the next one is also 10 newtons, but they act in an opposite direction. So you're explaining that one arm of the coil experiences a downward force, that's CD. The other arm experiences an upward force, which is upward, sorry, right? So these two forces, they form something called a couple, right? So based on those two forces, guys, what direction is this coil rotating in? Clockwise or anti-clockwise? So that's something else they want in the answer. You need to say that the two forces, they create something called a couple, right? That's a term in physics. They create a couple, and the coil is going to move either clockwise or anti-clockwise. So everybody's saying clockwise here, so that's correct, right? So the coil is actually rotating this way, right? If you look at the forces, look at this force here, and look at this force. It's going to cause the coil to spin in a clockwise direction, right? So sometimes they ask you that. So all of that you're going to put in your answer, you know. This is about 9 marks to explain how this thing working, right? Now, one key thing that you need to indicate here, there's a reason why we use a split ring, right? Now, when the coil flips, right? So this is what's happening. The coil, right? The coil is going to rotate in a clockwise direction. However, when the coil, if we didn't have a split ring there, what's going to happen is that the coil is going to keep doing this, left, right. It's going to move clockwise, anti-clockwise. The coil is not going to rotate if you didn't have that split ring there. The purpose of the split ring is to ensure that the coil rotates in one direction only, right? That's an exam question. Why do we use a split ring? The purpose of the split ring is to ensure that the coil rotates in one direction only. If you don't have the split ring, what's going to happen? The coil is just going to go back and forth, right? Now, that's basically what the simple DC motor is. So you have to be able to sketch a diagram, right? You have to be able to sketch a diagram, and you have to be able to explain how it works, right? Now, they didn't say anything about AC generators, but they could. This same circuit here, what you could do, right? The same circuit, what you could do, right, is actually, one second guys, I know who's trying to call me. Yeah. What you could do, right? They could ask a question like this. This is a simple DC motor. And if I want to convert this into something called an AC generator, right? There's a modification I need to make in order to convert this thing into a simple AC generator. All I need to do is to remove the split ring, right? So you remove the split ring and you use something called slip rings, right? So basically it's two rings side by side like this. So using two slip rings in order to convert this into an AC generator. And if you want to get power from the AC generator, all you need to do is to find a way to make the coil rotate. There are several ways you can do that. You can attach a windmill to it to make it rotate. You can let water flow through something to make the coil rotate. Once you get the coil to rotate, you're going to produce an AC current, right? Some of the things they ask you about the DC motor as well, they can ask you, how can we make the DC motor spin at a faster rate? In order to do that, what we can do is increase the current flowing through the coil. That's one, right? That's one thing we can do. We can make sure we have more coils. That's a second thing we can do, right? And what we can also do is to increase the strength of the magnet, right? So these are things that they could ask you in the exam, right? So be aware of the various things that could be asked in the exam, right? So guys, this is all the time that I have available today, right? And like I said, this is my last free physics session, right? So if you haven't done so as yet, like I said, please hit like and hit subscribe, right? I hope that the 4 sessions was of help to you guys, right? The only 2 sessions I have left, I have a chemistry session and I have a math session, right? And that's Monday and Tuesday next week. Okay, so I hope you all found the session helpful. All right, guys, so that's it for me. Any question before I go? All right, so my piece of advice to you guys, make sure, and you see these topics here, these topics that CXE gave you all. Let's go back to the beginning here. You see this here? Make sure you can handle all of these things that they have here, right? I have gone through most of these things, but make sure that you all can handle or answer these questions, right? I've covered everything here in the 4 sessions, you know, everything that is required, right? All right, somebody's asking about CAPE. No, unfortunately, I don't do CAPE, right? I just don't have the time to fit it into my schedule. All right, so all I do at the moment is maths, chem, phys, add maths at the CSEC level. All right. All right, guys, so that's it for me. You guys take care, enjoy your afternoon, and good luck.